Okay, we're going over the stoichiometry mass to mass homework. Let's go through this. Here we go. How many grams of sodium and chlorine are needed to produce 2.5 grams of sodium chloride? So 2.50 grams of NaCl. I first need to get the molar mass. Molar mass is 58.5, right? That's 1 mole. Then I need to do the mole ratio. I'm going to do sodium chloride to sodium, so it's 2 moles of NaCl. Let me zoom in so y'all can see what I'm doing. Is equal to 2 moles of Na, and 1 mole of Na is equal to 23 grams of Na. So grams and grams cancels out there. Moles and moles cancels out there. Moles and moles cancels out there. So everybody, I need your help. What is 2.5 divided by 58.5 times 23? What? Speak up. Come on. 9.80 because it needs to be 3 sig figs. 9.83 times 10 to the what? Grams of sodium. Is that right? Yes, Carson. Yeah, do that on your way here. 2.50 grams of sodium chloride is equal to, or excuse me, is going to be having 1 mole of NaCl on top, 58.5 grams of NaCl on the bottom. 2 moles of NaCl is equal to 1 mole of Cl2. Cl2 is going to be 71 grams per mole. Okay, what is 2.5 divided by 58.5 divided by 2 times 71? I'll take your word for it. Any questions? Are there any problems that any of you would like me to specifically target? Let's go about it that way. Yes, David.
Can we go over number 8, please?
Sure. Number 8. All right. Where's my calculator? There it is. So first we need to check to see if this equation is balanced. It is not balanced. So let's put a 2 there and a 2 there. Is it balanced now? 2 leads and 2 leads. 4 oxygens, 4 oxygens. It looks balanced to me. Any disagreement? Oh, that's number 7. Whoops. Let's take a look at number 8. Oh boy. This balancing took you 30 minutes? Let's see. All right, so maybe we need a little scoreboard here. So I'm going to write this on my notes on the side. Have a piece of paper right on. Let's try it out. All right. We have 1 zinc. We have 4 oxygens. And we have 6 hydrogens. And we have 2 carbons. On the product side, I see 1 zinc. I see 2, 4, 5 oxygens. Hydrogens, I see 6. And carbons, I see 2. All right, let me check those numbers here. Hydrogen, 6, there's actually 8 hydrogens. And oxygens, there's 2, 4, 5. Okay. So we have hydrogens there. Let's try putting a 2 right there. Did your water have a 2 in front of it? Yeah. Okay, working. We're getting somewhere. So that's going to cause our hydrogen number to bump up. Let's see, 6, 8. So you have 10 hydrogens now. And you're also going to have, let's see, 2, 4, 6 oxygens. Okay. 1, 2, 3, 4. Let's see. 1, 2, 3, 4. 1, 2, 3. Did your zinc acetate have a 2 in front of it? No? All right, I'm not going to bother there. Let's see. Oh, I put that in the wrong spot. Did your methyl acetate have a 2 in front of it? Okay, that's what I was meaning to go for. Okay, we have 2 carbons now. Actually, we have, 2 carbons now. No, 4 carbons. We got 6, 7, 8, 9. Wait. 6, 7, 8, 9. 2, 4, 6. I think I miscounted somewhere. 8. No, there's still. How many hydrogens are on the left? Well, we got 6 there, 7, 8, 9. There's 10. Where's the? I see that 2 times.
6, 7, 8, 9.
Oh, duh. You got it. Yeah, so that's 10. Wow. Staring me in the face. It's balanced, right? It's done. Okay. Yeah, so sometimes some of them take a little longer than others. Do a little scoreboard. Get your tallies going. All right. So this one looks like it's going to have to take a lot of space. So I'll do one thing at a time. So zinc acetate is this guy. That is zinc acetate. So we are basically converting zinc acetate to everything else. So the first one I'll do is zinc hydroxide. So we have 3.66 times 10 to the second grams of ZnCH3COO2. The first thing that you need to do is you need to find the molar mass. So I'm going to ask you guys for help. What did you calculate the molar mass of zinc acetate being? What did you get?
I got 183.4.
Derek says he got 183.4 grams per mole. Can someone confirm that? 183.4 grams is going to be over 1 mole. And I guess we can try to squeeze this in here. CH3COO2 ZnCH3COO2. Okay. Now we need to look at the molar ratio. According to the equation, there's 1 mole of ZnCH3COO2 under 1 mole of zinc hydroxide. Ooh. I'm going to run out of space. I'll have to put it here. And just keep an eye on what math I'm doing. We then have 1 mole of zinc hydroxide. What did you guys get from the molar mass of zinc hydroxide?
99.4.
Can someone confirm that? 99.4. All right. Okay. So for zinc hydroxide, here's what we got. What I would do, if you get a little confused by the scientific notation, take it out of scientific notation. Do you know what 3.66 would be in standard notation? 366. So 366 divided by 183.4 times 99.4. The answer for the first one, and I'm going to write it up here somewhere, for ZnOH2, you should have gotten 198 grams. And you could also said 1.98 times 10 to the second grams for that substance. Are there any questions with the first substance? Zinc hydroxide. There it is. And there's that answer. Anything? Are we good? All right, let's go on to the next substance. Methyl acetate. Or no, acetic acid. That's called acetic acid, CH3COOH. All right. There we go. Here we go. I should not have erased the molar mass. Derek, what was the molar mass? 180 something?
183.4.
What is the molar mass of acetic acid, CH3COOH? 60 even?
Yes.
All right, so looks like we do 366, or you can do 3.66 divided by all that stuff. Divide by 183.4 times 2 times 60. So I know I'm not being very helpful by plugging in the substances here, so here's what I'll tell you guys. If you just pay attention for me. Pay attention here. I'll try to make this understandable. I'm going to use an asterisk to represent ZnCH3COO2. That's going to go here, and that's going to go here. And it goes here. There's 1 mole of that substance right here. You see that? There's no number right there. That means the number is 1. There are 2 moles of acetic acid. Acetic acid is CH3COOH. And over here, you're also going to have CH3COOH. And up here, you're going to have CH3COOH. So the answer I have for CH3COOH is 239 grams, which you can also write as 2.39 times 10 to the second grams. Any questions with that? Did I do that right? Arshan.
Can you go back to the first one? No, like the first question.
I'm still working on this one.
Oh, yeah.
I'm not done with water.
Oh,
It said only find the reactant.
Oh, all right. Well, fine. I thought it said products. All right, fine. What do you need, Arshan?
We got a different answer for the chlorine.
What did you get from the molar mass of chlorine?
71.
What did I do wrong?
Well, we got 1.52. Yeah,
2.5 divided by 58.5 divided by 2. 2.5 divided by 58.5 divided by 2 times 71. All right. I see. I got it.
Wait. Hold on.
Whoops.
That's for just like, it's that's for just like chlorine like by itself. I wrote it. It's like grams of Cl2, right?
Yeah, but 71 isn't it 2?
One mole of Cl2 is 71 grams.
So like, just put it in grams of Cl2. Why do you have to like change it back to just regular Cl?
I'm not changing it back to Cl. Cl2 is 71 grams. 1 Cl is 35.5. You multiply it by 2, you get 71. Cl2 is 2 atoms of chlorine. So this right here is 71.0 grams per mole. That's what's done right here. That's diatomic. It has to be Cl2. Just like have no fear of ice cold. That's the C, Cl2. What's the problem, Kevin? Okay. David, did that help?
Yes, sir.
Anybody else? Derek?
Could you do 9 and 10?
Okay. 128 grams of methane when combusted. CH4 will produce how many grams of each product? Okay, this is a combustion reaction. CH4, what do you need to combust? O2, CO2, H2O. There's the unbalanced equation. No, wait. Yeah, 2, 2, 2. I know. I don't think that's right. Let's see. Carbon, carbon, that's good. Oxygen, oxygen, that's not good. Hydrogen, hydrogen. So I see 4 hydrogens. Let's put a 2 up here. Now we have 4 hydrogens. How many oxygens are on the product side now? 4. So let's just put a 2 there. Is it balanced now?
Yeah.
That's better. Okay. 128 grams of methane when combusted will produce how many grams of each product? Okay. How many grams of oxygen are used? So you have to do all 3. You have to do oxygen, CO2, and water. I'll have to do one at a time. One mole of methane should be 12, 13, 14, 15, 16. 16 grams of methane. 1 mole of methane is equal to 1 mole of CO2. And 1 mole of CO2 is 44 grams. Okay. 128 divided by 16 times 44, I got 352 grams of CO2. Anybody else get that? Derek? Okay, so I'm going to erase this work. And do the next substance. The next substance is water. 2 moles of water on top for the second step. And I wanted you guys to memorize this. What is the mass of water? 18 grams. Trust me, you're going to be dealing with it so much, it's best just to memorize it. So for water, that is 128 divided by 16 times 2 times 18. I got 288 grams of water. Did you get that?
Yeah.
Okay. And for oxygen, it says how many grams of oxygen are used. So let's plug in oxygen here. For oxygen, there are 2 moles of O2. 1 mole of O2 is equal to 32 grams of O2. And so we do 128 divided by 16 times 2 times 32. I got 512. Did you get that for oxygen? Okay. Any questions on 9? Yes, Arshawn.
Don't you know, like, the products, could you just, like, use algebra to figure out the last grams?
Sure. Okay. Number 10. 690.0 grams of ethanol, C2H5OH, when combusted in air will produce how many grams of each product? Okay. I'm going to write that balanced equation on top, so just so I have room for it, because I'm running out of real estate. And after this one, we have to get started with our new material. So we have, this is another combustion reaction, so C2H5OH plus O2 yields CO2 plus H2O. And I want you, some of you may be sitting here thinking, how do you know that that's the reaction? Well, the fact that it says combustion means that it needs oxygen. So there's the oxygen. Ethanol has carbon. So one of the products is carbon dioxide, and the other product is going to be water. That's how I know. All right, let's check for balancing. I see 2 carbons on the left. I see 1 carbon on the right. That's a problem right there. Put a 2 right there. I see 6 hydrogens on the left. I see 2 on the right, so let's put a 3 right there. And now let's count up our oxygens. We have 1, 2, 3 versus 4, 5, 6, 7. So I should put a 3 right here. Is it balanced? 1 to 3 to 2 to 3?
Yeah.
Okay. Here we go. it will produce how many grams of each product? So I just have to worry about these two. This should go by pretty quick. C2H5OH. Oops, how many moles? 690 grams of it. So let me try to do this in my head. 4, 12, 24. 24 plus 16 is 40. 46? Is this 46 grams per mole?
Yes.
All right. All right, there's your setup. 690 divided by 46 times 2 times 44. For carbon dioxide, I got 1,320, which we need to fix because that's only 3 sig figs. We need to get it to 4, so we can make that pretty simple. Grams of CO2, but here it is in proper scientific notation, 1.320 grams, excuse me, times 10 to the 1, 2, 3, times 10 to the third grams of CO2. 1,320 is 3 sig figs. You need to get it to 4 sig figs because 690.0 is 4 sig figs. So if you just shift the decimal 3 places to the left, you'll have 1.320 times 10 to the negative third grams of CO2. Questions? All right, last one. We're going to plug in 3 moles of water now. 1 mole of water is equal to 18 grams. 690 divided by 46 times 3 times 18 is 810 grams of H2O. That is only 2 sig figs. So let's shift the decimal to the left twice, 8.100. You just add another 0 there to make it nice. Times 10 to the negative second grams of H2O.
Isn't it positive?
Oh, yeah, it is positive. I don't know why I did that. Yep. Is that good?
Yes.
Yes, sir.
All right. So if you guys have any other difficulties with this, be sure that you let me know. Mass to mass is the hardest of the 3. Moles to moles is easy. That's 1 step. Moles to mass and mass to moles is 2 steps. That's like the intermediate level. And then mass to mass is the hardest at 3 stages. Okay. Let's get into some new stuff. Where's my notes? Okay. Today, the topic on the agenda is limiting reactants. So, question I have is, why do reactions stop? Jade, you go out on a shopping spree, and what is one of the reasons that your shopping spree could be considered over?
No more money.
You ran out of money. That is going to be your limiting reactant. You have the energy to shop all day long. But if you run out of money by noon, your day is over. So in a chemical reaction, remember that RXN is an abbreviation for reaction. There is generally a reactant that is in excess. Back in the 90s, when I was a kid, we had the weirdest thing. Hot dog buns came in packs of 8. Hot dog wieners came in packs of 10. You always had 2 extra. It was the dumbest thing. And they finally corrected it. I don't know why they were doing it. Maybe they just had too many pigs or wherever they get the hot dogs from. But if I wanted to have if I wanted to have a hot dog, which is the hot dog wiener and the hot dog bun, what resource would I run out of first? The buns, obviously. I would run out of buns. So the hot dog wieners would be called your excess reactant, and the hot dog buns would be called your limiting reactant. So the reactant that is used up first is called your limiting reactant. So I want to make some hot dogs. What does the number of hot dogs that I want to make depend on? The amount of buns or the amount of wieners, given the fact that the wieners are the excess and the buns are the limiting? All right. So here's a pretty important point, pretty simple, pretty obvious, but let's just get it out there. The amount of product, in this case, hot dogs, depends on the reactant that is limited. Some of you play on the Plant High School football team. Let's say that there are 50 sophomores that go out for the football team. Plant only has 42 helmets. Ooh. They have 42 helmets. They have 35 shoulder pads. What's the limiting reactant? Players, helmets, or shoulder pads? Yeah, you have 50 players. You have 42 helmets. You have 35 shoulder pads. You can only dress 35. You can't have somebody go out there with a helmet, no pads. So that's basically how the limiting reactant is the one that really dictates or controls how much product you make. And just, again, another obvious point, reactants that are left over are called your excess reactants. It's what stuff you have left over. All right, so how can you determine which reactant is limiting? And we're going to start calling it the LR. I tell my AP Bio students, you're not allowed to use abbreviations if you don't know what they stand for. Like in my AP Bio class, and we were talking about hydrogen bonds. A kid said, can we just write H bonds? I said, only if you know what it means. If I ask you what's an H bond and you say, I don't know, then you're not allowed to use it. So if you guys are going to use LR, you better know it stands for limiting reactant or you're not allowed to use it. How can the limiting reactant be determined / calculated? Well, let's do a test run. Okay. Here we go. Oh, first off, let me give you an equation. Let's say we have the equation sulfur, which is a liquid, S8, reacts with 4 moles of chlorine, which is a gas, to yield 4 moles of disulfur dichloride, which is a liquid. Let's check real quick, and I want you guys to confirm if it is balanced or not. You always have to check. Max, is this equation balanced? Yes, it is. Okay, great. So the first thing you guys need to be sure is you need to check the equation for balancing. Luckily, in this particular example, it is balanced. So move on. All right, here's the information. If 200.0 grams of sulfur, which is S8, reacts with 100.0 grams of chlorine, what mass of disulfur dichloride is produced? So we're all clear. Remember, I'm taking you through. This is the training wheel session. This is one of your reactants, and this is your other reactant. Your question is, what mass of disulfur dichloride is produced? And that's that final substance. Okay, guys, you ready? I'm going to give you the keys to the castle. This is how you do it. If this step is already done for you, then you can skip this step. But the first thing that you need to do, step 1, convert mass to moles. What conversion will you need for that? You will need the molar mass of each substance. That is correct. So you will need the molar masses. Well, for sulfur, that is 32.1 grams per mole, if I'm not mistaken. And for chlorine, that is going to be 35.5 grams per mole, if I'm not mistaken. No, hold on. I'm not done yet. I got it. I'm not done. How many sulfurs are there? There are 8. So what is 32.1 times 8? 32.1 times 8 is 256.8. There's that. Any questions? Arshawn, Nicole, is that what you were going to say?
I was also going to say chlorine.
What? Oh, oops. Oh, am I doing okay so far? All right, have the right substance? Okay. Now, we have Cl2, but hold on. Cl2 times 4. How many total chlorines is that? That's total of 8. Yes, Nicole?
Yeah, I think
Oh, yeah. Oops. That is right. That was my bad. So there you go. Oh, wait, moles.
that was right.
I got it. I know. Okay. Let's do this. I got it. How many grams of sulfur do we have? How many were given in the problem?
200.
200 grams of S8. 256.8 grams of sulfur, S8, over or under 1 mole of S8. So 200 divided by 256.8. You got 0.779. Better? There we go. Converted it to moles. Sorry for the confusion. Okay? Now, 1 mole of chlorine is 35.5. You have 8 of them. So what's 35.5 times Do you have 8?
Yeah, 2.
Two.
Yeah, you have 2. I'm thinking of something else. Yeah, 2. So that is 2. So that's going to be 71.0 grams per mole of Cl2. And that is going to be the substance right there. How many grams of chlorine were we given? 100 grams of chlorine. So we got 71.0 grams of chlorine on the bottom, 1 mole of chlorine on top. 100 divided by 71. I got 1.41 moles of chlorine. Okay, there. Now, there will be problems where you will be given moles right off the bat. So you can skip that step entirely. Lucky you, if that happens. Yes, Juliana?
Why is it that sulfur by chloride is like
That's the molecular formula. Remember, molecular is where it's not reduced yet? If it was empirical, it would just be SCl. We're good? Okay. Now, step 2. Use mole ratios. Find the mole ratio. How many moles of sulfur were there? Okay. How many moles of chlorine were there?
4.
So you can say 1 mole of sulfur to 1 mole of chlorine. Another way to say that would be 1 mole of sulfur is equal to 4 moles of chlorine. That's your mole ratio. Now, is this the actual mole ratio? That's what we're going to get to next. So you guys need to take the larger number, which is 1.41 moles of chlorine, and you're going to divide it by the smaller number, which is 0.779 moles of sulfur. So I'm going to write that down. Divide the actual ratio. The actual ratio, if you don't see it, that's why you converted, is 0.779 moles of S8 is equal to, what do I have, 1.41 of chlorine. That's the actual ratio. And so you're going to divide the actual ratio. Large number is going to be over the smaller number. And so for that, we're going to have 1.41, we can put a 0 at the end if you want, moles of Cl2 divided by 0.779 moles of sulfur. This is a new step. 1.41 divided by 0.779 is going to result in 1.8 moles of chlorine per 1 mole of sulfur. So here is why you did that step. You want to get one of those numbers down to 1. So you can say that one of them is just the whole number. So here is what this interprets as. Hold on. 1.808 moles of chlorine is available for every 1 mole of sulfur. So let me ask you this. You need 1.808 moles of chlorine for every 1 mole of sulfur. You're going to run out of chlorine first because you need more of it than what is available. So in this case, chlorine is going to be the limiting reactant. Yes, Derek. 1.808 would round the same. That's not going to really change our answer all that much. 1.81 would be fine. Yes, Arshan.
Isn't that more CL? Why is it limiting?
So only 1.080 or 1.81 moles of chlorine is available for every 1 mole of sulfur, instead of the 4 moles of chlorine required by the balanced equation.
Oh.
So the chlorine is going to run out first. Or not, the chlorine is going to run out first.
Okay.
Kevin?
Don't you still need like a whole mole of SA? You only have 0.77.
So you're going to run out of the chlorine before the sulfur. The sulfur is going to be what you have left over because you're going through the chlorine faster. And that's going to result in it being used up first.
It's in the same ratio though.
It's not the same ratio. 1.8 to 1 is not the same ratio. It's a 1.8 to 1 ratio. Yeah.
I don't understand how, isn't there more chlorine than sulfur?
Where are you getting that? Are you going by the mass?
Well, the last.
The 200 to the 100? Or what? Where are you getting that from?
You said 1.8 moles of chlorine is available for every 1 mole of sulfur.
Mm-hmm.
So there's more chlorine available for every mole of sulfur.
So that's saying that you are going to have, or you're going to need. Here's the difference between have and need. The amount of chlorine available is going to be 1.808 or 1.81. The amount of sulfur is going to be 1 mole. So when you are going through this reaction, you're going to be requiring more chlorine to get the reaction accomplished. You need more chlorine compared to the sulfur. So you're going to go through chlorine faster.
How do you know you need more chlorine now?
Because that's going to be, compared to the sulfur, it's being used up more. So I can definitely sense there's a lot of confusion here. So let's try this. I'm going to work through this problem, and there's more than one way to skin a cat. I'm going to break this down, and I might run out of time in class because we only have 5 minutes. So this sounds like it's definitely going to carry over into tomorrow, and I'll definitely have this. We'll figure it out tomorrow if we don't get through it today. But I'm going to solve this problem. I'm going to show you that when you actually convert to the products, because you'll actually be able to calculate the amount of reactant based on the limiting or product based on the limiting reactant or the excess reactant. You guys are asking the questions, and I'm really happy you're asking the questions, but you're asking the question kind of halfway through the process. And so I have a feeling that when the whole process is through, you're going to realize, oh, now I see it. So it's kind of like asking questions halfway through a movie where you got to let things kind of play out, and you're going to see it for yourself. Me telling you that chlorine right here is limiting reactant, you could say I kind of got a little ahead of myself because I was going ahead and giving you the answer before we actually got into how to mathematically determine that was the limiting reactant by completing the equation. So here's what I think we should do. We have about 3 minutes left in class. We're going to pick up exactly where we left off here tomorrow after your vocab quiz. And we're going to get this straightened out where some of you, I heard you whisper, I'm so confused. I don't want that to happen. So I'm going to get this all straightened out, but if I continue on this path, we're going to run out of time. So here's how we're going to handle it. We're going to do it tomorrow. We'll pick up exactly where we left off. There's no homework tonight except work on your review and study for your vocab.